So in today's video, we're going to be talking about implicit differentiation. And before we get into that, I just wanted to make sure you guys understand the difference between um, an implicit equation and an explicit equation, and also a single variable equation and multivariable equations as well. So when looking at single variable equations, when we're talking about any equations, you have a dependent variable and an independent variable. In this case, your dependent variable is y and your independent variable is x. And basically, if we're talking about an explicit equation, your dependent variable can be separated from the rest of the equation and stand by itself. So that's what makes it explicit. In this case, you can see y basically stands by itself. So this is an explicit equation. But when talking about an implicit equation, in this case, y is still your dependent variable as well. But you can see y cannot be separated from the rest of the equation. As you can see, this tangent of xy, there's no way you can separate this y from this x. So that kind of all jumbled up together. So this is what makes this an implicit equation. Now looking at a multivariable equation where you don't just have an implicit and an explicit equation, but you also have an implicit or explicit variable, a dependent or an independent variable, you also have something else. So in this case, your dependent variable is z, but you have two independent variables, all right? And this is what makes this a multivariable equation. And basically what makes this explicit is that your dependent variable z can still stand by itself, but what makes this implicit is that your dependent variable z, all right, cannot be separated from the rest of the equations. And that's a short summary on what separates an implicit from an explicit equation. So now, before we dive into some examples and how we can best understand implicit differentiation, I just want to make sure you guys understand three things: the product rule, the chain rule, and the quotient rule. And basically, if you do not have a good understanding of these three rules when it comes to differentiation, make sure you check out my other video that I talk about these rules before watching this video, and I'll put a link to that video in the description. All right, now, okay, if you understand these three rules, then let's dive into some examples. All right, the first example I'm gonna use is basically a very simple example. So if you have an equation x to the fourth power plus y squared, all right, equals to 12x, right? And in this case, this is a single variable implicit, or a single variable explicit equation. And we could just get this dependent variable to stand by itself on one side of the equation and then differentiate, or we could just do implicit differentiation as it is. And that's the trick. And not just a trick, but the good thing with implicit differentiation is that you can use implicit differentiation on equations which do not necessarily just require that type of differentiation. Like, you could differentiate this explicitly, or you could do it implicitly. All right, let's do it implicitly. And basically what we'll do is, if you're trying to get dy dx on this equation, so basically what you do is you differentiate x to the fourth power, and that's going to give you 4 x to the third power, right? Plus, you differentiate y squared, and that's going to give you 2y dy dx. And basically, when you come across any of these types of equations and you have to differentiate implicitly, basically, if when you're differentiating the dependent variable in this case, which is most likely going to be y, you always have to attach dy dx to that. So continuing on from there, if you differentiate 12x, you're gonna get 12. Right? Basically here we've already differentiated. We've already gone through differentiation. So from here, you just want to have dy dx stand by itself on one side of the equation. So the rest is just basic algebra. If we subtract 4x cubed on both sides, we're gonna get 2y dy dx equals 12 minus 4x cubed. All right, and then we'll be left with dy dx equals 12 minus 4x cubed over 2y. All right, and if we divide by 2, we're going to get 6 minus 2x cubed over y, and that is your answer. As simple as that. Moving on, let's solve a different example, a little more complicated. And this example will be x squared plus 2xy plus y squared equals to 5. And this is a single variable implicit equation, all right? So the first step basically is differentiate this equation. And if we differentiate x squared, we're going to get 2x. We differentiate 2xy. Now this is the tricky part. In differentiating 2xy, we're going to have to use a product rule. All right, so basically, keeping x constant, we differentiate y, we're going to get, or keeping y constant, we differentiate x, we're going to get 2y. All right, and then plus keeping x constant, we differentiate y, we're going to get 2x. And differentiating y is just 1 dy dx. All right, and then plus, if we differentiate y squared, we're going to get 2y dy dx equals to, differentiating a constant 5 will give you 0. Differentiating any constant will give you 0. And then basically from there, we just want to basically group dy dx or the dy dx terms, and then send everything to the other side of the equation. All right, so we can have dy dx stand by itself. So we're gonna get we're gonna send 2x and 2y to the other side of the equation. So we're gonna have 2x dy dx plus 2y dy dx equals negative 2x minus 2y. All right, and then if we factorize out dy dx, we're going to have dy dx equals negative 2x minus 2y, all of that divided by 2x plus 2y. All right, and if we divide everything by 2, we're going to have basically negative x plus y all over x plus y. All right, and if we cancel this, this should just give us negative 1, and that is your answer. All right, now moving on to yet another example. All right, 6xy minus y cubed equals to 10. All right, and now before solving this, I want you guys to take a minute and try pause this video and try and solve this by yourself. All right, now getting into it. If we differentiate 6xy, again here we're gonna use the product rule, and basically keeping y constant, differentiating x, we're gonna get 6y, plus keeping x constant and differentiating y, we're gonna get 6x dy dx. All right, minus keeping and then differentiating y cubed, we're gonna get 3y squared dy dx. All right, and then this is going to be equal to 0. Now we want dy dx to be left alone. Factorizing out dy dx, we're gonna have dy dx into 6x minus 3y squared, and then sending the 6y to the other side, negative 6y. All right, and then we end up with dy dx equals negative 6y all over 6x minus 3y squared. And yet again, that is basically your answer. Let's do another example. All right, if we have dy dx equals x, y. In this case, you might look at this and say, well, this is not implicit differentiation, and you're right. But at the same time, you're wrong. And this can be implicit differentiation as well. So basically, if you have this, looking at it, we're gonna use the quotient rule, all right? And basically, what is the quotient rule, all right? If you have an equation u on v, all right, basically to be able to differentiate this equation, with respect to v, all right, what you're gonna do is basically you're gonna say, all right, keeping the bottom constant, all right, differentiate the top, minus keeping the top constant, all right, in this case I think this is differentiating with respect to u, keeping the top constant, you differentiate the bottom, divided by bottom squared, all right, and then, all right, following on to this, differentiating this equation, basically differentiating dy dx, you're gonna get d squared y dx squared equals, all right, now if we differentiate this side, keeping bottom constant, differentiate the top, minus keeping the top constant, you differentiate the bottom, all right, divided by bottom squared, okay. And basically we know what dy dx is, so we're going to take this from here, all right, and insert that here. So we're going to get y minus x into x on y divided by y squared, all right. And basically here we just have to multiply out, so we get y minus x squared on y over y squared. And if you want this to look prettier, we're just gonna multiply the top and the bottom by y, and it's just gonna give us y squared minus x squared all over y cubed, all right. So the final problem we're going to solve is sine of xy equals to 3. And this is probably going to be the hardest of all the problems we've solved so far. And basically you have an implicit form inside of the sine, all right. In this case, we're going to have to use the chain rule and the product rule, all right. So basically, the first thing to do here is to use a chain rule to differentiate this. And then if we start from the outside, all right, cracking this shell, let's start from the outside. So the sine, so we're going to have the differential of sine is cosine, all right. And then since whatever is in here just remains the same, so xy, all right, and then that multiplied by the derivative of what is inside, so the derivative of xy, and this is where we use a chain rule. And basically this is going to be, if we keep y constant, differentiate x, we're going to get 1 times y, plus keeping x constant and differentiating y, we're going to get x times 1 times dy dx. And then from here, our objective is basically to have dy dx stand by itself on one side of the equal sign. All right. So from here, we're basically going to subtract both sides by y cosine of xy. So we're gonna end up with x dy dx cosine of xy equals negative y cosine of xy. And then we divide both sides by x cosine of xy, and then we're going to have dy dx equals negative y cosine of xy divided by x cosine of xy. All right, and then from here you just notice that cosine of xy cancels out, and we're just going to end up with negative y on x, and that's the answer. Thank you.